between two or more objects through forces. Now this is a very general definition. Now I'm making the definition intentionally vague or intentionally wide. Why? Because our idea of collision is that you have an object and you hit it, right? And that's a collision, right? Or you have a car and then someone hits it, that's a collision. But the definition of what a collision is, or the applicability of what we're going to learn, is much broader than that, right? For example, if you consider you have an object from space, right? So outside of the solar system comes close to the sun, right? So we know that due to gravitational attraction, the object is going to bend its trajectory, right? It's going to go around the sun somehow, right? And so if we consider the object coming from far away as having an initial momentum, right? That interaction through the gravitational force with the sun that makes it goes a different way, and then it goes far away in some other different direction, then that process of, okay, you're coming in this way and then you're coming out that way, the object never touched the sun, right? It never collided with the sun, but it changed the sun, the interaction with the sun changed its direction, right? And this happened over a long period of time, yes? But still, you can apply the rules that we're going to use, we can apply that as if it were a collision, right? And we're going or we would describe that situation just like we're going to describe the collision between an object and another, okay? Does that make sense? It also applies to other objects, like say, when you have an electron beam, right? So electrons are tiny particles, the smallest stable particles we have, right? And if you have an electron beam, so you're shooting electrons at some material, right? The electrons never actually collide with the material you're shooting them at, right? I don't know if you knew this, but electrons will never touch another electron, right? Because as they get close to them, they just move apart, right? And they want so that basically makes them just move around the object. They go through the material, but they don't actually hit the material. And so the interaction there is through the electromagnetic force or the electric force, right? And so you're going to have forces that control the interaction, and we treat that as a collision, as if we were just throwing a ball against a wall type of deal. All right? So the same idea. So the other important fact here is that of these two forces over a time interval. And that's, that should be obvious because we're going to use this idea that the change in momentum happens because there is a force acting over a certain time interval, right? So in the case of the comet, it may be months, right? You have an object from space coming out of the solar system, approaching the sun. When that force between the sun and the object starts becoming noticeable, right, because of the distance, then that's where the timing starts. That's the collision starts, right? They interact with each other, and then now it's far away again, right? And so that's where the collision ends, maybe months or years, okay? Or if you're talking about the electron interacting with an atom, that may be nanoseconds, right? Or less than that, okay? So the time interval can vary greatly, right? But there are some restrictions to that, okay? So we're going to see that in a second. Now collisions come in two flavors, let's say. So one of them is called the elastic collision. And elastic collisions are collisions where the kinetic energy is conserved. Right? So what does conserved energy mean? What does the conservation of energy mean? Is the what? The energy isn't lost.
It can't be destroyed.
Say that again? So in general, so if you think of mechanical energy, right? That's the correct statement, right? So you don't change your mechanical energy. This one is a little bit more so a little bit more simple. So the change is zero, right? Or the final value of the energy is the same as the initial. Okay? Now, the individual parts of your system may change their energy, right? The energy may not be the same for each individual component, but the total energy of the system remains constant. That's the important part during elastic collisions, right? Now, in inelastic collisions, what you have is that you have these are collisions where the kinetic energy is not conserved.
So where's it go?
See that again?
Where's it go?
So where does it go? That's a good question. So inelastic collisions are collisions where the energy is used to either deform the objects, so change the shape of the objects, or the shape of a configuration. The other reason to lose or gain energy is, say, if you consider an inelastic collision, an explosion in reverse, right? So if you have an explosion, let's say you have a grenade, right? So if you activate the grenade and then it explodes, yes, then of course you have more energy at the end than you had at the beginning in terms of kinetic energy, right? Because now you have shrapnel just flying in all directions, right? So each of those pieces has kinetic energy, whereas before you had nothing, yes? So you definitely have an increase in kinetic energy, a change in kinetic energy, but the momentum, even in that system, the momentum remains constant. So if you were to add the momentum, the vector momentum of each of the pieces, and you add all of them, you should get zero at the end. Okay? The addition of all the momentum of each of the pieces of your system would add up to zero in that type of situation, right? So when you say where does it go, right? So if you have a collision where you have energy that and two objects that change shape, like say a car crash, right? Your car gets deformed, metal is bent and all that, right? Or you have say two sticky balls, right? And so the change in shape is that the two objects coalesce, right? Then that's where the energy is spent, right? So if you have taken any biology class, are you guys taking chemistry or biology yet? So you have seen that whenever you have a chemical bond, there is energy associated with that bond, right? And so if you break a chemical bond, you need to spend energy to break it, right? Because there is energy associated, potential energy associated with the bond. So it's the same idea, right? So in order to bring or bind things together, you need to spend energy. Okay? So that's what happens here in inelastic collision. So those are the conditions for elastic and inelastic collisions. Now let's study a little bit what happens when we change the momentum, and then look at a couple of particular situations we're going to study. So when we change momentum, then we said the change of momentum is the net force times the time interval. All right? So what is the condition for momentum to not change? So if the momentum is not changing, then what can I say about the other side of the equation? Is what?
Not changing.
Well, but so if the time doesn't change, then there hasn't been any time to change, right? So that cannot be the answer, right? So if momentum is conserved, if momentum doesn't change, then what can I say about the right side of the equation? Say what? No, even if there is a collision, if the time doesn't change, sorry, the momentum doesn't change, then what has to be true on the left side of the equation? No. Time is changing. Time is constantly changing, right? So if you have a collision, you have a before and after. So there has to you have change. What is zero?
The force.
And if the acceleration is zero, then the net force is zero, right? So if this guy is zero, then necessarily the net force has to be zero. Yes? So if the net force is zero, then the question we have to ask ourselves is, what is the net force? You guys remember what is the net force on a system? Okay, that's the definition of force, yes, but when you're calculating the net force, what do you have to do? Add and what?
All the forces acting on the object.
All the forces acting on the system, right? So that's absolutely right. So let's look at an example. So one example we've done before. So we have two boxes, box 1 and box 2, sitting on a table, right? So in that example, we would have said, okay, we have weight 2, we have weight 1, we have normal 1, 2, we have normal 2, 1, and we have the normal 2 ground. Yes? And those will be the forces between in that system. Yes? Because we have two different objects. But if I tell you that I want to make that system, the 1 and 2, just a single system, then I can visualize this as just a single object that has a single weight that interacts with the ground with a single normal force, okay? And that's it, right? And the internal forces we don't have to consider. Does that make sense? Right? So this is two systems separated, right? So this is system 1 and system 2. And so for system 1, I have a set of forces. For system 2, I have another set of forces, right? But if I look at them as one thing, yes, then I only have two external forces. One is the interaction with the ground, the other is the interaction with the earth, and that's it. The interaction between 1 and 2 is no longer important because both of them are part of my system. All right, so those forces are no longer external to the system. Does that make sense? Yes? If you remember in the lab, the lab we did last time, you know, that was the same approach we had when we had to work on the equation, right? So we separated these guys in, so you have the weight, we have the other weight, we had a normal force here, we had the frictional force here, and we had tension right here and tension right here. Yes? So those were the forces that we had. But the task that you guys had was to make it so that these two blocks work as a system, right? And we obtained the equation that ended up being the weight of this guy minus the friction force on this guy equals mass plus mass B times acceleration, right? And those are the only two external forces, right? This is the interaction between the earth and this block, right? Or my system, right? It's pulling the system this way, yes? And this one here, the force of friction, is the interaction between the table and this guy, the system. Both of those are external. These two forces, the normal force and the weight, they cancel each other out. Even though they are also external, they cancel each other out. So what changes? What did I get rid of? The internal forces, right? The tensions that are the same. So they work as an action-reaction pair almost. Make sense?
So you saying just we can just do it like that from now on when it pertains to momentum and stuff.
So no, it's not like we are going to do that from now on. But for the purpose of collisions, we are going to consider the systems to include the two objects. All right. So instead of thinking about the forces of the interaction between the two objects during the collision, we're going to think or only consider the forces that are external to those, okay? So if you have a collision between two cars, right, we don't care about the force between the cars while they are colliding, right? Even though that's the biggest force, that's not what we are going to focus our attention on. We're going to focus our attention in the momentum properties, all right? And so to do that, what we're going to do is we're going to say those forces are internal to the system. So those forces will not change the momentum of the system as a whole. Does that make sense? If those forces that are the biggest ones are internal, then those forces are not responsible for any change in my momentum. Okay? And so the only forces that are external to that would be able to change my momentum. Okay?
So everything in your scenario, everything but like the collision that would be making a difference.
Correct. Correct. So in that scenario, the collision, which is the biggest forces at play, only those external forces to those are the ones that may change the momentum. And then here comes the kicker, or the important part with the time factor. Typically, collisions happen over a short period of time. So remember the example we did with the baseball, right? What was the time of the interaction between the bat and the ball? Something small, right? 0.7 milliseconds, right?
Yeah.
Or less than 1,000th of a second. All right? So that's a tiny, tiny, tiny number, right? It's a very short time. Now, while that was happening, we could have argued that the ball would have experienced the force of gravity, right? So during that time, the force of gravity would have acted over the ball, right? But how big is the force of gravity over a baseball? It's the mass times gravity, right? What is mass of the baseball? Is 0.14, right? More or less, 0.14 kilograms, 0.15 kilograms. So the weight of a baseball is around 1.4 newtons, yes? Do you remember how big the force between the bat and the ball was after we calculated it?
It was a lot, right?
It was like a truck,
Yeah,
like 1.3 times 10 to the 4th newtons, right? Or 13,000 newtons, yes? So that's 10,000 times bigger.